Good afternoon. So we spent 2, maybe more lectures on Chern-Simons theory as an abstract field theory with some amazing properties, including how it describes degeneracy of the ground state on a torus, how it describes statistics of quasi-particles, and how at the edge of the space, if there's an edge, there are gapless excitations described by a chiral boson, at least for the abelian case, characterized by a set of integers. Anyway, so we had a good discussion on Saturday morning on various aspects of Chern-Simons theory. Or any questions? I mean, what we're going to do today is now the next lecture and 2. We will now suddenly have a lot of power. We're going to apply what we learned and find out and describe many interesting physical states that have all been observed in the real world. Well, in a manner of speaking, most of them. Any questions? Okay, so let me begin actually with a relatively straightforward application, at least to the extent I'm going to cover it, which introduces an example of what are now called SPT states. So, and the simplest state, so here this SPT stands for Symmetry Protected Topological Order. So we're going to describe certain quote unquote topological states. They're topological in the sense that they have gapless excitations, protected excitations on the boundary of the sample. But unlike the states that we have considered so far, the condition for the states of the boundary to be present is that there has to be a certain symmetry. I guess the Z2 spin liquid also requires certain symmetries to have edge states on the boundary, but the Z2 spin liquid also has topological order in the bulk. It's got anyons in the bulk. So the SPT states, at least in the convention that developed, are states which do not have any anyons in the bulk. So all the interesting stuff is really confined to the boundary, the exotic stuff. Okay, so you need some extra symmetry. So the simplest example is sometimes called the quantum spin Hall state. Some cousins of it that we're going to discuss in a few minutes have been observed, of course, in many experiments. So the way you get such a state is you imagine that you have some material with electrons with lots of spin orbit coupling. So we have large spin orbit. So because of this, spin up and spin down electrons need not obey a very simple Hamiltonian, which is independent of spin. In fact, in general, when you have spin orbit coupling, they'll also be termed that flip spin up to spin down. So even the spin quantum number is not really well defined. The only thing that's conserved is the total angular momentum. But if you're in a crystal, you have broken rotational symmetry, so there is no angular momentum either. And fundamentally, the only thing that spin orbit interactions allow you to preserve is time reversal symmetry. Okay, but nevertheless, let's imagine a very simple model where the spin up and spin down electrons are separately conserved. So spin up and spin down are separately conserved. Okay, so this is just a model. It may be in some material this could be approximately true, but it's never really true, because the same thing that gives you different band structure for spin up and spin down, which we're going to require, also gives you a spin flip scattering, which we're just ignoring for now. Okay, so you have some material which spin up and spin down are separately conserved. So now that means that there's a larger symmetry. Normally, the only symmetry you have is the U1 symmetry of a conservation of total number of electrons. But now you have U1 cross U1 symmetry. So that's the larger symmetry that we're going to consider, which is give you this very simple quantum spin Hall state. Okay, so all right, so now imagine that somehow by luck or by design, you manage to have the spin up electron moving in a band structure which has a non-zero Chern number. So I think in one of your sections you learned about the Haldane model, and that's a Hamiltonian on the honeycomb lattice, which can give you a band with a non-zero Chern number, even in the absence of an applied magnetic field. So we say that, let's imagine that spin 1, spin up, is in a band with Chern number 1. So what's spin down doing? Well, spin down will, by time, if you have time reversal symmetry, is very likely to, it has to be then, if in the presence of time reversal symmetry, to have the opposite Chern number. Because, you know, under time reversal, you complex conjugate the bands, and the Chern number, of course, changes if the hopping matrix elements go to their complex conjugate. It reverses sign. All right, so that's the condition under which you get what's called a quantum spin Hall insulator. And now, from everything you've learned, you can quickly deduce its properties. You know, so you have C up is +1 and C down is -1. And then we know that if you now take these Chern bands, they're going to have edge states. Any band with a Chern number has an edge state. And there'll be an edge state for the upspins, which maybe goes clockwise, whereas the edge state for the downspin goes anti-clockwise, because it has the opposite Chern number. And we also know how to describe the edge states using a Chern-Simons gauge theory. What we do is you couple a gauge field to the particles, and then when you integrate out the particles, you get a Chern-Simons term for the gauge field. So here it's useful to couple a gauge field separately to the two particles. So you have gauge field A up mu and A down mu, which couples with to the up and down spin particles respectively. So basically then you have a CS theory for this very CS theory, which is n equals 2. You have two gauge fields. And notice I'm writing them as capital letters because they're not really emergent gauge fields. They're supposed to be viewed as external probes. They're not strongly fluctuating. Okay, and the K matrix then, because the K matrix gives you a Chern number 1 for the upspin and a Chern number -1 for the downspin, is in fact the Pauli Z matrix. And really, that's all there is. So now you have a topological state with this more complicated K matrix than the simple one-dimensional K matrix for the single integer quantum Hall state. Now it's a two-dimensional matrix, but it's kind of trivial. Just one species of particle has spin up, and the other has Chern number 1, and the other has Chern number -1. You can also check now if you just turn the crank and apply everything we have learned about Chern-Simons gauge theory, is that this theory is trivial in the bulk. It doesn't have anything interesting going on in the bulk. There's no anyons in the bulk. The determinant is 1, modulus of it. So there's no ground state degeneracy in a torus, so no surprises there. And also from our Chern-Simons theory, we know it has edge states. One of them is left moving and the other one is right moving. So in fact, this is just like non-interacting electrons on any wire, except because the number of up particles is separately conserved from the number of down particles, you know, the two edge states are perfectly protected. They're always present. Nothing's going to destroy them unless you destroy the conservation law. So the key thing that protects the edge states now is this U1 cross U1 symmetry here. Okay. All right, so that's a lot of time to spend in a fairly trivial construction because it seems to rely on a rather artificial symmetry. Okay, but of course the whole, people were talking about such states, but hadn't fully understood the generality of the idea, and it was really an amazing paper by Kane and Mallet, a couple of papers, 2005 or 2006, that made a key point. The main point they made was that if you have time reversal symmetry, then in fact this U1 cross U1 symmetry is not required. That is, you could even have spin flip scattering, provided you preserve time reversal, you would still have these two edge states. You would still have this edge theory. So this edge theory would continue to work even if you did not conserve U1 cross U1. So the U1 cross U1 is not required, as I say here. The U1 cross U1 symmetry is not required. And you would still get the same edge state theory as you have over here. Okay, so that's really properly the quantum spin Hall insulator, and it's protected, as we say, it's a symmetry protected topological state, meaning that there has to be some symmetry to protect these edge states, and that symmetry is time reversal symmetry. Okay, so what's the main idea? So it's easy to actually see the idea when you think in terms of what's happening on the edge. So on the edge, you have spin up going this way and spin down going the other way. Okay. Now, the question is, can there be some impurity or any scattering that will take a spin up electron coming this way and flip it down to spin down electron going the other way? The short answer is no, because the time reversal partner of a spin up going that way is really a spin down going the other way. So anything that since they're time reversal partner, anything that takes one to the other will break time reversal symmetry. There can't be any perturbation that doesn't break time reversal symmetry, because time reversal commutes with this operation, with the symmetry. Well, sorry, I didn't say that right. Let me try to say that a little more explicitly. So suppose you did have a term like this. Suppose you had some impurity which flips a right moving particle to a left moving particle. Suppose you had such a term. Well, then this would, give you some scattering matrix elements, and these two edge states would basically disappear. They'll annihilate and get some finite energy, and you'll be done. Okay. So, however, this term in the Hamiltonian is not permitted by time reversal symmetry. And the reason is, of course, the left and right are up and down spin indices. So I should really be writing this as psi dagger up times psi down. And you can see that this is not allowed, because under time reversal symmetry, if you try to do the symmetry in a way that it also flips the spin, C up goes to IC down, whereas C down will go to minus IC up. And if you take this transformation and put it in here, you find that it's not allowed. So single fermion backscattering term is therefore forbidden, and the edge states remain gapless. Okay, so that's the start of that observation is the start of a very long story. There's books have been written on it, and I possibly can't go into it. And it's all, mathematically also quite sophisticated. There's this nice book by Bernavig and Taylor Hughes, which covers quite a lot of this. So this is the simplest example, is what is now called a Z2 topological insulator. And here the word, and it should not be confused with the Z2 spin liquid, which are very different animals. the Z2 spin liquid doesn't have this K matrix, doesn't have these protected edge states. It has a K matrix which is off diagonal, which is 0, 2, 2, 0. This is 1, 0, 0, minus 1, if you, at least the corner spin Hall version of it. Okay. So in particular, what Kane and Millay pointed out was that there was a generalization of the Chern invariant, so the Chern number. So right now what we've been using is just taking the same thing we learned from the fractional quantum Hall effect or the integer quantum Hall effect, and said, well, whenever you have a Chern number, you have some edge states. So if you want to, so somebody asks you, can you look at the bulk and tell me if I have edge states? Well, the way you can look at the bulk and tell you have edge states is just compute the Chern number of the bands. If you have a Chern number, then you know you have edge states. So there's a Chern invariant, which tells you that there must be edge states anytime the Chern and you go to a boundary. So another question you can ask is there an invariant, which is not the Chern invariant? Because once you have spin flip scattering, then your only symmetry is U1. You don't have U1 cross U1. So there's no way for you to write down these two Chern numbers, one for spin up and spin down. They're all mixed up with each other. So is there some invariant which generalizes the Chern number? And this is what was first written down in this paper by Kane and Millay, the second paper actually. And what they pointed out was there is a invariant. It's rather complicated to write down in general. It's analogous to the Chern number, but it involves computing a quantity which has only two possible values, 1 and minus 1. So that's hence the group Z2. So that's why these are called Z2 topological insulators. And this Z2 invariant exists both in 2 and 3 spatial dimensions. Okay. All right. Well, you could really teach a whole course on this Z2, as with many other things in this course. So I'm not going to say much more about this. In fact, really not much more. Tomorrow's section, how you will cover an even simpler example, which has a Z2 invariant, which are systems in one dimension. So in one dimension, it's not sufficient to have time reversal symmetry, but if you have a particular particle hole symmetry, then that also turns out to have a Z2 invariant, and you get protected edge states. So this is in something called the Su-Schiefer-Heeger model, which was known 20 years ago or longer. And it wasn't until Kane and Millay that people realized that the Z2 invariant of the SSH model has generalizations in higher dimensions, in 2 and 3 dimensions. One more thing I say, why is it D2? So just to give you an idea of why it's Z2. Suppose you had, just happened to have many bands, so that they were n, the Chern number was n for spin up, and the Chern number was minus n for spin down, where n is not just 1, but some other integer. So then you have a total of 2n edge states, n moving to the right and then n moving to the left. But now if you turn on the spin flips term in the spin orbit coupling, how many states will be left? Well, the answer turns out that only 2 in general are protected. You don't protect all n of them. There's only this, this is the minimal Hamiltonian that's protected, and everything else will be gapped out. So instead of having 2n edge states, you'll just have 2 edge states, one moving to the right and one moving to the left if you turn on spin flip scattering. And that's the reason one of the reasons it's called a Z2 invariant. And where does the 2 come from? Well, the important property of this Lagrangian or Hamiltonian is that at 0 momentum, if you take k equals 0, then there's a double degeneracy. So if I draw the band structure, can do it over here. So you have, if you look at the edge state, so this is the edge of the sample, the momentum along the edge, and this is energy. Then the upspins electrons have a dispersion this way, they're moving to the right. These are the up spins. And the downspin electrons have a dispersion this way, moving to the left. And all I'm saying is that the fact that they cross here is protected by time reversal symmetry. And in fact, you can see, so at this point, there's a doubly degenerate state at k equals 0. So k equals 0 is a special point because it's what's called a time reversal invariant momentum, or TRIM. You'll see the word TRIM in all these papers on topological insulators now. So meaning that, under time reversal, the velocity of the particle goes v2 minus v. So if it's at rest, well, it's a time reversal invariant state for the particle. So at this time reversal invariant momentum, time reversal symmetry requires a double degeneracy, and that's called Cramer's theorem, which I won't prove, but you can look it up. So there's a Cramer's degeneracy for spin-a-half particles or any half-integer particle. In the presence of time reversal symmetry, if you have spin-a-half or half-integer spin, you have to have a twofold degeneracy. So that's the reason you always have at least two levels crossing at the time reversal invariant momentum. Now, when you take the full crystal into account to figure out this Z2 invariant, you then realize that there are other momenta, and this is what was pointed out by actually Fu and Kane. No, it was already in the Kane-Mallet paper, yeah. That there are other momenta which are time reversal invariant on a lattice. So on a 1D lattice, one time reversal invariant momentum is of course k equals 0, but k equals pi is also a time reversal invariant momentum, because under time reversal, pi goes to minus pi, but minus pi is the same as pi modulo the reciprocal lattice vector. So to fully understand the protected edge states, you have to look at the Cramer's degeneracy and various parity quantum numbers at these time reversal invariant momenta. And you'll see an example of that, in fact, even in one dimension in section tomorrow. Okay, that's really all I have to say about topological insulators. Not because there isn't much more to say, but it would take a lot of time, and the theory does become rather intricate. It's a lot of very careful analyses of symmetries, especially time reversal, which will take the rest of the semester, at least, if I want to go and describe it in any detail. But this book by Pernavig and Hughes is a good reference. Okay, so that concludes this chapter. Any questions? And finally, the third reason is I'm not an expert on this topic by any means. So I would, if you ask me a difficult question, I may not be able to answer it. All right, so then let's go back to the main theme of the course, which are at least one of the main themes, which is true topological states, meaning bulk topological states, where there are anyons in the bulk. And now we have all the technology to now get many other interesting examples. The only example you've seen so far in any detail is the Z2 spin liquid, and now we're going to see a lot more. So let's just return to our favorite problem. I'm going to describe this first in the context of our favorite problem, or at least my favorite problem, which is spins on a lattice in 2 dimensions, or equivalently, hardcore bosons at half filling. Okay, so if we could be looking at this spin model, whereas SI is a spin a half on some, let's for now we even take the square lattice. And you can of course rewrite it in terms of hardcore bosons capital B at half filling. Okay. So this is the kind of theory we want to study. And among the phases we met for this particular class of models, we're also going to allow now, break this Heisenberg symmetry down to down to just time reversal symmetry in general. And in fact, even consider cases without any symmetry. Where was I? Okay, so we've learned many interesting phases of bosons that have filling. One is the charge density wave, the checkerboard state. Then there's the valence bond solid state. There's the Z2 spin liquid. Of course, there's a superfluid state, which in this spin language corresponds to some kind of long-range order in the spins. But now we're going to meet one more today, and and another in a little while. So in fact, there's a whole zoo of phases, but they can be understood, topological phases in kind of unified way. So let me try to make a table to give you a global picture of where we're going and where we've been. So I'll just use the spin language, just a little simpler. So the way we did things before was we took our spin and we want to get a topological phase. So we factorized it using bosons, which I called S. These are the Schwinger bosons. Oops. Little s on each side. So we do this on every side. I'm not writing out the site index. S dagger alpha beta sigma S beta. Turns out you can also do this using fermions, which is what we'll use today. F dagger alpha sigma F beta. And in the simplest case, there's a constraint. Sigma alpha beta, sorry. And there's a constraint here that S dagger alpha, S alpha equals 1 that we met before. And similarly, the constraint on the fermion number F alpha equals 1. And this gives us a U1 gauge invariance. Under which these spin-on operators, S alpha goes to the e to the I rho times S alpha. And here, F alpha goes to the e to the I rho times F alpha. Okay, so, a natural question might be, well, which one should I choose? Well, the answer is, well, it really depends on what type of topological phase your system has. And which one it has is not an easy question to answer. You have to put it on the computer and figure it out. But if you have an inkling of what kind of topological order it has, then that will guide you on how to use what's called the parton construction. So these are the two possible parton constructions where we're taking our spin or a hardcore boson and splitting it into these partons, either the S partons or the F partons. So let me make a table of the different states that we've seen and are going to see using this parton construction. Okay. So let's see. I'm gonna try to see. Okay. So the simplest case we looked at was we used the Schwinger boson partons. And the key property of that Schwinger boson partons to get the Z2, well, first we had a U1 spin liquid, right? So there you had on the square lattice, you had this gauge symmetry. So you had a U1, so you had two sublattices, and on A sublattices, SA goes to e to the I rho SA, and on the B sublattice, this went to e to the minus I rho SB. So A and B are the two sub-square lattices, and under this, the parton Hamiltonian was invariant under this construction. So here I'll make a column for, let me make it over here, the gauge group. So the gauge group here that was left unbroken because of this gauge symmetry in the part on Hamiltonian is still U1. And here I'm going to write out the fate. What is the final phase that you obtain? Let me just say phase rather than fate. What is the phase that you obtain? Well, so this is in fact the first case we met, but it turns out to be the most difficult one. Well, not the most, but it was the more subtle. And here, so what happens is ultimately this thing is unstable. You don't get any topological phase. It's unstable to VBS order. And this is something we'll see in a week or two. Okay, so that's case number one. So this was the square lattice Schwinger boson. I should have written this down. So this is only on the square lattice. Okay, so that's case number one. Now let's take another case. We take the triangle lattice for Schwinger bosons. This is also something we met. And in the triangle lattice, what we found was that there was some part on Hamiltonian. And in this part on Hamiltonian, there was only a Z2 gauge invariant. So Zi on any site could go to plus or minus 1 Si. And then the part on Hamiltonian was invariant. And so then the gauge symmetry here was Z2. And what you get here is the Z2 spin liquid. Okay, so that was our one success of a topological phase so far, which we have described on the triangular and other lattices too in some generality. Okay, so now, so that's the list of things we've done with bosons. So let's try to do it with fermions. Which is so one of the things you can do in using fermions is to first of all just have fermions hopping on a site, and that's what we're going to see today. So, and when they just hop around, so we have fermions hopping, or the F should be, I shouldn't say fermions, the F partons, F hop. And then the turns out that the resulting Hamiltonian has an emergent U1 gauge symmetry, e to the I rho Fi alpha. So that symmetry is okay. So the gauge is U1. And these could hop in some background flux, as we'll see, in some flux, some emergent mean field flux. So we're going to see that today. And here the answer is a bit similar to this. It's either unstable, either it's just totally unstable, or it describes a QFT, or it describes a gapless conformal field theory. So that means it's some critical state. Maybe it's describing a phase transition or maybe some critical phase. It's the kind of thing we haven't met yet. And again, we're also going to meet this. All right, so that's one of the things the fermions can do. I'm going to run out of space here. Okay. Another thing fermions can do is just like the bosons did in both these cases, is that they can pair. So FF, FI, FJ, they form a BCS type condensate, is not equal to 0. So we haven't gone through the details of this, but you can work it out. And we might see some examples later. So this thing has a gauge invariance, which goes to plus minus 1 Fi. And in fact, it's almost exactly the same as the bosonic case. So now the gauge symmetry is Z2. And what you get is a Z2 spin liquid. So now you can ask the question, there seem to be two different ways at ending up the Z2 spin liquid, one here and one here. One where you take bosonic partons, and other case you take fermionic partons. Which one is the right one? Well, the answer in many cases people have shown it doesn't matter, because the Z2 spin liquid we know has two types of excitations which carry a Z2 gauge charge. One is the E particle, the other is the epsilon particle. So when you do this bosonic parton construction, you get the spin-on becomes the E particle, and the epsilon particle is the bound state of the spin-on and the vison. When you do it over here, the parton becomes the epsilon particle, and the E particle is the bound state of the epsilon and the M. And people have shown in great detail, in some very beautiful work, how you can get the same state in the sense of all its properties, either starting with Schwinger bosonic partons or fermionic partons. All right. So finally, let me get to the really new states that we're now going to meet. Okay, so we continue this. Still using fermionic partons. And we're going to just do a very simple thing to this case, the U1 case, where we're going to say, I'm going to do another color. Yeah, the fermions hop around, the fermionic partons hop, but the band structure hop in a band with Chern number. So this is the trick. So this is how we're going to get some non-trivial physics with anyons. We're going to take our partons, not the actual electron, which the actual electron moved in Chern number, in the integer quantum Hall type states. But now we're going to we take our electron and split it into partons, and we make the partons move in a Chern number. So here there's still a U1 gauge symmetry. So this will still be U1. And what we're going to meet here is the chiral spin liquid. So that's where what we're going to discuss now. What happens when you take your partons and make them move in a flux, in a Chern number band. And the most interesting case, or the most difficult one, comes about when you take all of this and combine them. So what we have learned here is that there's two ways of getting a stable gapped spin liquid state. One is to take your partons and pair them up. If you pair them up, you get a Z2 spin liquid. The other is to have them move in a band with non-zero Chern number. And then you will get the chiral spin liquid. So how about we do both? So if you take a general model where the F are paired. So you still have Fi, Fj is not equal to 0. And you have the Bogoliubov particles. So the Bogoliubov, the paired, after you do pairing, you have some Bogoliubov particles, which is now, people call them Majoranas. And these Bogoliubov particles move in a band with Chern number. And also in quotes, I will say that you need spin orbit. You need, if you keep the spin orbit term, this doesn't quite work. For details, for reasons you will see by the time I'm done with this. So we need spin orbit. Okay, so we're going to fractionalize the spin into fermions. Notice that to play with Chern number, I need fermions. It's hard to have bands of bosons with Chern number. I mean, bosons can move in a band with the Chern number, but if the bosons have a band, they just condense. So it's hard to get bosons with Chern number type things. So that's why we're using fermions. And that's the power of using fermions, is that it gives you a whole another handle to get more complicated phases. So if your spin-ons, first of all, they pair like they do in the Z2 spin liquid, and they also have a Chern number as they do in the U1 spin liquid. So you combine the two features. Then, of course, the gauge symmetry is still Z2, but this is the famous Kitaev-Ising non-abelian spin liquid. So this is the Kitaev non-abelian. Which everyone is hoping to see in experiments. There are some signs of it, but not entirely convincing. Sometimes people call it ITO, for Ising topological order, because there's a conformal field theory that describes the edge, which turns out to be related to the critical point of the 1 plus 1D Ising model. It's just a free Majorana fermion. It's half of it because it has a chiral conformal field theory. Okay, so my hope is in the next week or two to describe all of these things. We won't do the gapless. The gapless will be the next chapter, but now we want to describe the chiral spin liquid, also the fractional quantum Hall states, which are closely related, and then the non-abelian Ising topological order. All right, so is this table clear to everyone? This gives you a roadmap of what we're going to talk about over the next couple of weeks. Any questions on this table?
So I have a quick question to the comment.
Sure.
You made before here that we don't work with bosons because if they get a band, they just condense. Could you? So what does this mean exactly?
Well, I mean, so suppose the boson, so you have some emergent gauge field and you want your gauge field to acquire a Chern-Simons term. That's the trick. You have to have some emergent gauge fields. You have to make them occupy a Chern-Simons term. So the way we get that to happen is that you get a band and you fill all the states in the band. So you have to fill it with fermions. And when you integrate out the fermions in a band, then you will get the Chern-Simons term. Now with bosons, you don't fill any bands. They might pair and form a gap state. The boson excitations are always unoccupied states. If they were if there were states below 0 in energy, they would just condense. So all the excitations, all the states associated with the Fermi boson Hamiltonian have to be positive in energy. So that means they're not really occupied. So they could be in gap boson excitation with a non-zero Chern number, but that's not going to give you any Chern-Simons term because those states are not occupied.
Oh, okay, I see. So it's just like directly just because like fermion statistics like kind of force us to stack them on like fill level, like one level after another.
Another way to say it is that when you compute the Chern-Simons term, you compute the Chern number of all the negative energy states. Those are the ones that have fermions that are occupied. It's the negative energy states that give you the Chern-Simons term, not all of them. I mean, if you have a band structure with fermions, the sum of the Chern numbers of all the bands is 0. It's only the occupied states which have negative energy that give you the Chern number. But with bosons, you can't have negative energy states because the boson will just condense into them. So that's the power of the fermion. They give you a whole different handle on how to get some non-trivial states.
I see. And so maybe a naive question would be like, can we do this decomposition as well with something with like anionic statistics directly, or wouldn't or just doesn't work?
Okay, people have tried such things. Gives you a mess. So I'm, so people have worked on different constructions of topological phases for 20 plus years now. All kinds of things have been tried. I'm trying to encapsulate all of that in what I think is the best way to do it and unify them. So it turns out, in the end, I believe that one of the first approaches, which got a bad reputation for a while, is the best. It's the parton construction. And as far as I know, every state that anybody's ever discussed can be described using the parton construction. And it's usually the simple, at least for me, I mean, this is my own bias, I guess, since I've worked with it a lot. It's usually the simplest way to understand what's going on. I mean, the point is that you have to have a phase with emergent gauge fields to have any topological order. And because they're emergent gauge fields, it must be that there's some gauge charge matter. And so might as well introduce the gauge charge matter right at the beginning. So you see what your gauge fields are, and then so it seems like you're introducing new degrees of freedom when they aren't that aren't physical, and that's why people vary of this. But once you understand how to deal with strongly coupled gauge fields, which I think we do now quite well in 2+1 dimensions, it's not that bad. It's when you just you do these things here. You just, as we'll see, you see if there's a Chern-Simons term. You see whether the discrete unbroken symmetry. You look at monopoles, which I'll do over here in the next chapter or next 2 chapters from now, so on. Okay.
Thank you.
All right. So now let's get moving then. So so we're just going to take this. So what I'm going to describe now is both these cases, not the Z2. This case here, which we'll just mention in passing, but then go on to the chiral spin liquid, which is easier to deal with, in fact. So what we do, so we take this decomposition, and then we plug it in here, and then we do Hartree-Fock factorization, and you get some free particle Hamiltonian for the fermions. So yeah, I guess I've spelled it out here. This is the spin-spin interaction, which is a 4 Fermi term. We're just turning the same crank as we did for bosons. You decouple it with this link with this bond field Qij, and now we're going to decouple it in not p dagger b dagger, but f dagger f, because we don't want any fermion pairing. If you see with bosons, we were driven to have pairing, but otherwise the boson would just post condensed. But with fermions, no problem. You can have no pairing and still get a stable state. So you just have fermion hopping here. With the Qij as a conjugate variable. You just assume the Qij is some constant in just the mean field theory, and then we look at fluctuations of Qij. All right. So first thing you want to do is understand the mean field theory. So you're going to get some band structure for the fermions. And so now it's up to you to find out what what's the value of epsilon 0 and the Tij. And the way you do it is you just actually do the calculation. You take this mean field Hamiltonian, you minimize the energy of the original Hamiltonian and put it on a computer, and lots of people have done that for us. So we're just going to, and it's an approximate calculation anyway, since it's a mean field, so we're not sure we can trust the results. So we just proceed with some big guesswork as to what are interesting Tijs that you get. So anyway, if you do the calculation, people have shown is that what you do is you get this kind of, I put both first and second neighbor hopping, you get this kind of Hamiltonian. So this is the Hamiltonian we're going to study. So first of all, ignore the second neighbor terms. Then just have T1. And the T1, you'll notice, are not all the same. They've written down here in what's called the pi flux configuration. If I take the product of T1 around any loop, I get a negative number. You get minus T1 to the fourth. T1 is real, and T2 is also real. So there's pi flux per plaquette of the square lattice. Now, pi flux is the same as minus pi flux. So this thing doesn't break time reversal. It's time reversal invariant. And so that's the famous pi flux state on the square lattice where you only have nearest neighbor hopping, but with pi flux per square plaquette. And I've chosen a strange gauge. It's not even Landau gauge or circular gauge or anything like that, but because the next calculation becomes a little simpler once in this particular gauge. Okay, so that's the saddle point solution with pi flux. Okay. So you can go ahead and then determine the spectrum. And when you determine the spectrum, you find that it's sort of like graphene. So in the pi flux state, if you just diagonalize it, and the diagonalization is done over here. This is the Hamiltonian. Ignore the T2 terms, but just the T1 term, the 2 by 2 matrix. You diagonalize it, and it turns out in the gauge that I have that at plus or minus pi over 2. So what the dispersion spectrum you get looks something like this. This is Kx. It goes from I think pi to minus pi. This is 0. You get 2 Dirac nodes. So this direction is E, and that other into the is Ky. And you get another one over here. Of course, they meet up in some way. Actually, I have an actual picture here, but where the nodes are gapped. So these are the 2 nodes here. There's one here and one here. This is a picture when there's a small gap, which is what T2 induces. But for now, okay, imagine that that's an actual conical point and another conical point there. Okay, so that's the dispersion of the pi flux phase. It's basically like graphene. It's got 2 Dirac nodes. So this is concerning because now you have 0 energy fermionic spin-on excitations. So all the stuff we said, well, if the spin-ons are gapped, we can integrate them out and we get some nice gauge theory that we can deal with. We can't do that safely here because there's no gap to the spin-ons. So this is the reason we won't consider this any further. Although one thing I should say in the minute remaining, what are the fluctuations? So yeah, spin-ons are gapless, so that means we're not going to get a topological state, because by definition, the topological state has a gap. This is gapless. Strictly not a topological state. But okay, but what are the fluctuations? What are the flux? So now this Q is only in the nearest neighbors. What are the fluctuations? Well, the fluctuations, there we go. Yeah. So now you notice here that if I do this gauge transformation of the F that I just showed in my big table, the Q transformed now with opposite signs here and there. And because they have opposite signs, actually life is very simple. You remember the phases of Q were the gauge fields, and here the gauge fields are just very simple. You just take a line integral from one point to the other, and on each link you put a gauge field so that you parameterize it this way. And A is just a constant on a link. And then you can see from here and here that the gauge transformation of A is exactly just the gradient of rho. So then you just have an ordinary U1 gauge field. Okay. So what is the theory of fluctuations? Well, it turns out to be very simple. You have these Dirac fermions now written in the most confusing particle physics notation. Psi bar psi, gamma mu d mu psi. And then you have a U1 gauge field coupled to it. And that's it. This M is 0 right now. So the theory of the staggered flux phase is massless Dirac fermion coupled to U1 gauge field. And that turns out to be quite a complicated CFT, which we'll have more to say about in the coming weeks. So we'll put that aside, and then turn to the case that gives you our first really interesting topological state here. That's suppose the numbers were such that T2 was also non-zero in this picture. And now I made this second neighbor hopping purely imaginary. And how did I make the choice? Well, the choice I made was, let's imagine that each square I said had flux pi. Now, it could be pi or minus pi, it didn't matter. But now let's pick pi. Because so suppose if we have pi flux through the whole square, then we can divide that into two. Half of it can go here and half of it can go here. Now, if I divide it into pi by 2, well, pi by 2 is not the same as minus pi by 2. So then I've made a choice, which means I've broken time reversal. So if you notice, if I go around, well, let's see. So this minus t, so if I go around this way, I get a -1 and I get an I. The arrow tells me going this way is I, so going the other way is minus I. So it's -1 times minus I get pi by 2. So if I go around clockwise around this triangle, I get pi by 2. And now you can check for every triangle here in this picture, this one or this one or that one or even this one. Every triangle has pi over 2 and not minus pi over 2. So basically I have a uniform magnetic field with flux pi over 2 per triangle. And that was the rationale between my choices for the arrows and the minus signs. Okay. And why am I putting this magnetic field? Well, as you can guess, because once you have a magnetic field, you're going to get a Chern number. The band is going to have a non-zero Chern number, and that's going to give you possibility of a very interesting topological phase, and the chance to use all the technology we developed in the previous chapter on Chern-Simons gauge theories. And you can do some numerics and find that this is a good choice, but you don't know until you've really done serious DMRG type calculations to see if this is actually works. This kind of state was in a very different language, first proposed by Laughlin and Kollmeier. And there was a lot of work on it, and people were skeptical because it never actually showed up in anybody's study of any spin model. But that has all changed now. In the last 5-10 years, there have been many examples of spin systems that have been proven to be in this state that I'm just pulling out of a hat over here. But it took a long time for that to happen, but now there's many examples. Okay, I'll stop there. And then definitely next time you will have a complete theory of the chiral spin liquid. Questions? Okay, if you want to, I urge you to take this, this Hamiltonian here, and the matrix is all written down here, and just play around with it, compute the band structure. Maybe if you really feel inclined, even compute some Chern numbers and see what you get. All right, so see you tomorrow morning at 9 if you want to join the discussion. Question,
Sorry,
yes.
Yes, it's like maybe not exactly the question related to the content, but I'm interested if you know of any reference, like when this kind of analysis of a Z2 spin liquid is performed, like together with all these numerics that you mentioned. If one would really want to trace, basically the whole story.
Well, there are two types of analysis. One is just a mean field decoupling where you just optimize energies. That's not reliable when you can do it. I mean, if you do that type of analysis, I guess for this model, this was probably done by Affleck and Marsden first, and then there was a paper by Wen, Wilczek, and Z. If you just limit yourself to this ansatz with first and second neighbor hopping, and you just minimize the energy, you will find that the flux is pi over 2 multiplicate. That gives you the best energy. That's definitely the case. That doesn't mean that particular model is going to form that phase, because that's just a mean field calculation. If you want to really find a model, and in fact, for the J1, J2 model in the square lattice, which is the first and second neighbor exchange, it doesn't exist. But then there's various, I think it was on the Kagome with first and second neighbor exchange, there were some models that people only recently found actual ground states, which are in the phase that we're just postulating here. Yeah, okay. I mean, if you send me an email or more specific, I can try to dig up some references. But the chiral spin liquid was kind of forgotten for a long time because people thought it didn't really exist in any reasonable model, but that's not the case anymore.
I see. Okay, thank you. Yeah, I will send you an email.
Yeah, okay. Okay then. See you tomorrow or next week or Wednesday.